At least we're a little bit cold outside, but it's not 2 foot of snow as it is over that at West Texas, which is why that class was canceled. They have 35-mile-an-hour winds and had 24 inches of snow this morning, but it was still blizzard conditions.
Dang it, why can't we have that here?
We may have snow and ice later this afternoon.
Yes! Look at this.
I don't care to have the snow, and I like snow, but the ice I could do with that.
Yeah.
All right, let's go and pick up where we left off. I wanted to do a few more things with the Bohr atom. Not so much with calculations, but talking about how to visualize that and things that it doesn't do for us. So, let's say that we had an atom, and we showed that we had these energy levels that we could find. So we have the n equal 1 level, n equal 2 level, n equal 3 level, and this value, depending on, is minus 13.6 electron volts. If it's hydrogen, if it's not hydrogen, then you've got a z squared to multiply it by. And then it goes down and so forth. Over this is minus 3.4 and so forth. A couple of things to know before we finish up. One is, notice that the gap here is bigger than the gap there. That is common for all Coulombic potentials. That is point charge type potentials. As you get further and further up, the energy levels get closer and closer together. We'll come back to that in a minute to say something about what we're going to do in the future. If you have an atom, such as hydrogen at least, then you had in this nucleus 1 proton. If it's not hydrogen, then you'll have Z protons and you'll have some number of neutrons. And then in the picture they did in chemistry class, they had that orbit, that orbit, that orbit, and so on. This orbit here is the n equal 1 orbit. It's also known as the K shell. Why K? Oh, everybody knows the alphabet starts with K. I don't know why it starts with K. I have no idea. I've never heard, but it does. So if you have an electron in here, that's the electron that would be in there. That's 2 different pictures. The one kind of showing the orbit, the other showing what we really need out of the orbit, which is how to calculate energy changes. If you had that electron go to here, that would be the n equal 2 orbit, also known as the L shell. Why? Because L's after K. Anybody want to guess what this one is?
J.
N?
Oh.
J, yeah. You didn't do too well in English class either, huh?
No, sir, that's why I'm here, hopefully.
M, N, O, so forth, okay? In X-ray stuff, a lot of times they talk about K alphas, K betas. The K means where you knock the electron out of. And if it's an alpha, it means that it falls 1 shell. So it falls from the L to the K. If it's a beta, it follows 2 shells. So it has more energy. Those notations occurred because they went back a long time ago, well before anyone had the Schrodinger equation or quantum mechanics. And they got into the literature and they've never gone away. In the same way, the 1s, the 2s, the 2p, and so forth occurred in spectroscopy before anybody solved quantum mechanics. So, for instance, a 1s orbit, there's the 1. The s had to do with the way the line looked when you were looking at these spectral lines. Some of them were very bright. They were called principal lines. And they turned out to be the P shell. There were some that went to very sharp. They were the S. Some looked kind of smeared out, diffuse. They got D. And some were incredibly fine, and they became the F. So depending on which transition they went, actually had something to do with the way the lines looked. But the numbering or the letters came from the way they looked in spectroscopy, not from the map. So consequently, you just have to remember all of these sort of things, because the chemists ain't going to change their ways. All right, they're already in it, they're doing it. So, you can think of it this way, or you can think of it in terms of an energy level diagram. Something else that can happen. If you have one of these guys, not hydrogen obviously, would need a lot of electrons, but let's say we had several electrons. How many electrons can you put in a 1s orbit according to chemistry class in high school? 2. So I could put, oops, give me a good pen. Where does the third electron have to go? Yeah, it has to go up here. Why? There's nothing in the Bohr atom that says that has to happen. You can put 65 down there if you want, according to Bohr. So the Bohr does not explain why the chemical elements have what they do, whether properties are the way they are, whether in certain groups in the periodic table like they do. It doesn't explain any of that. Quantum mechanics, which comes from the Schrödinger equation, will explain all of that. Bohr atom doesn't. It doesn't explain why some atoms are magnetic and some atoms are not. Now let's take the case of the quantum mechanics that says you can only put so many electrons in an orbit. If you start putting more electrons out other places, 6, 7, let's say 8 like that, and maybe one more out here for this particular atom. If you were to knock one of these guys out by any method, either heat it, knock it, whatever, smash it with an electron in an X-ray machine, so that guy gets knocked out. This guy can drop down, and he can emit a photon. And you can calculate what that energy of the photon is, according to this, if you knew what these energy values were for the Bohr atom. You could come in here and say that's the 2, and you could subtract the energy of the 1. You could find the difference, take 1240 eV nanometers, divide by the energy, find the wavelength. You can also do something else that's kind of interesting. Instead of emitting a gamma like that, it can appear to emit a gamma to this guy and send out another electron. In this case, that energy amount was set by that gap here. How much ever this guy gained by falling in. So he had that much energy. It took a certain amount of energy to pull that electron, this electron, out. Any energy left over goes into kinetics. So this energy of this electron is not continuous. It's unique. It's like a fingerprint, just like the gamma would be. There's a name for these. They're called Auger electrons. It's French, Pierre, like Auger. Now, there ain't none of those. I tried to find them when I was a student. All right. I had my Auger electrons, but I could never find out what the professor. He never wrote anything down. He just talked. I never could find the Auger electrons anywhere. All right. Those are the Auger electrons. Auger spectroscopy is a very powerful thing for looking for light elements. It's used routinely as a way of doing this. So you can look at the X-rays that come out by X-ray analysis. You can look at Auger electrons, which are much more common for light elements. Which one it does depends upon the element and how many electrons it has. Okay? All of that could be explained by the Bohr energy diagrams. But here's some things that the Bohr can explain about this. We will find out that there is no way for this photon to be emitted. And yet this electron comes out as if it absorbs it. So-called forbidden transitions. Bohr atom doesn't say anything about forbidding you from making it. If you have the right energy, you can make it. Quantum mechanics says, no, that's not true. Some lines will not exist. We find that in spectroscopy. So the Bohr atom is great about calculating energies, but it's not so good about predicting some things that we know. It was the start. It's not the end of the game. The Schrödinger equation is the end of the game. And that's where we're headed to. All right, with that, I wanted to knock off a couple more questions at the back of this test your knowledge and then move on. So one of them that I had in the back dealt with the question that if you really have quantized angular momentum, then why don't we see it in everything that has angular momentum? And the answer is, it should be there. If the electron has quantized angular momentum, then planets should have quantized angular momentum. But the question is the amount big enough to see that? Or is the amount so small that you experimentally cannot detect it, even though it's there? All right? So the question, which is basically a question out of Iceberg and Resnick's Blue Bible, is the following. Assume that the momentum of the Earth of mass 6 times 10 to the 24th kilogram, bring it in a little bit, due to the motion around the sun, is at a radius of 1.5 10 to the 11th meters and is quantized according to the Bohr relationship. What is the value of the quantum number? Well, L is momentum mv cross r. Since they're at right angles to each other for a circular orbit, it's simply mvr. Now my problem is they didn't give me the velocity. They don't need to. I know the time it takes the Earth, to go around the sun. I know what a calendar year is. And if I assume a relatively circular orbit, which is not a bad guess because Mars is the most eccentric of orbits and it's only eccentric about 6%, I think it is, then I can use 2 pi r for the distance, t for the time, and that way calculate roughly the velocity. Plug in 2 pi r, that's the circumference, divided by the period, times r. And that gives me 2 pi m r squared over t. And it says make that equivalent to the Bohr, which is n h over 2 pi. Solve for n. Okay, I took the 2 pi up with the other 2 pi, and that gave me 4 pi squared. I had the mass already. I had the r squared already. I took the h and brought it down. So I have time and h. Now, we've stayed with the 1240 eV nanometers because we've been dealing with atomic things. This is a big object, which, by the way, is a totally reason you shouldn't be dealing with h in the first place. But that's why they did it. So we're going to use SI units. The SI unit for h is about 6.63 10 to the minus 34 joule seconds. Close enough. 6.6 10 to the minus 34 joule seconds. The fact that I'm using this tells you that we probably shouldn't be doing quantum mechanics. And you can see that's really small. It's in the denominator. And on the top we have a mass of the Earth, 10 to the 24. We have a distance, 10 to the 11th, which is squared, so that's 22. So I have 22 and 24. So there's 46. I'm going to add 34 to it. This thing's going to have a huge number. I have 365 days approximately in a year, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. Put that all together and you get about 2.56 10 to the 74. That's your quantum number. That's a big dang quantum number. All right, it's not 1, it's not 2, it's not 3. It's huge. The Bohr correspondence principle says that when n is very, very large, or when h is very small compared to the things you're dealing with, then classical physics is what you get. Quantum mechanics will go to classical physics. So because there's so much angular momentum, and because increasing n by 1 doesn't change L very much, you basically have a whole bunch of levels that are very close together, and it's like looking at the grains of sand with your eye. You can't see that they're separate. They're too close together. To prove that, you probably wouldn't measure angular momentum directly, you'd measure energy. So let's look at the energy difference. If you just looked at the kinetic energy, in this case, the kinetic energy, so this is just K, We know that's within a factor of 2, the total. It would be L squared over 2I. I'm not going to put MR squared in for I or anything else. I'm going to leave it alone. The L is N squared H bar squared. If you looked at e to the n plus 1, the next level, then it would be n plus 1 squared H bar squared over 2I. So that would be the next energy level. With just a tad more angular momentum. By how much? By H bar. That's at 6.63 10 to the minus 34 divided by 2 pi. All right, so about 1 times 10 to the minus 34 more units of angular momentum. And then we're going to square that. Find out how much more energy. So if you take this and you subtract that, notice you can factor out the H bar over 2I, and it leaves you n plus 1 squared minus n squared. If you then divide by the original energy, all of this H bar over 2I is all cancels out. All that matters is the n plus 1 squared minus n squared and the n squared on the bottom. Well, n squared over n squared is 1. And the n plus 1 squared over n squared is not much more than 1. Well, you can find out what it is. You just go and multiply that together. So n squared plus 2n plus 1 minus n squared. So whack, whack, those two go away. And I get 2 times the quantum number plus 1 over the quantum number squared. Now, that's 2 over n plus 1 over n squared. And n is huge. So n squared, on the bottom, it's going to make that number really small. So I just forget that whole last term. So it's basically about 2 over n. If you multiply by 100%, that's what the number is. You need to measure to 7.8 times 10 to the minus 73%. I want to see that detector. That's got to be one hell of a good one. Like a few other problems like the uncertainty principle. All right, so you can't see it because the quantum numbers are so large that the spacing between them is so small that it's beyond any resolution of any detector you can make. So it doesn't mean it's not there. You just can't detect it. That means classical physics works fine. So why mess around with this quantum stuff? Okay? So if you don't need it, you don't use it. But it doesn't mean it's not true. Quantum explains everything. The large, the small, everything. Just like the relativity will explain freshman physics. But I don't think we want to make everybody use relativity to work kinematics problems in freshman class. Use the simplest physics that works for the problem. Now there's more stuff on the correspondence principle and how Bohr used this kind of as a rule of thumb to figure out what he was doing inside the book by Iceberg and Resnick. So I suggest that you read about it. I will not test that part heavily. I'll be more likely to test, can you draw me an energy diagram? Can you find me energies? Can you find me photons? Can you find me the wavelengths of those photons? Okay? But you do need to understand the basic correspondence principle. Yeah? Everything? Okay. One last thing before we totally leave this section and deal with Frank and Hertz. My little guy back here before, when we were talking about this atom, something else that the Bohr atom doesn't say is that if you put a couple of different atoms up here and you put them close together, there'll be electron-electron interactions, and these lines, their levels, do not like to line up. So if you had one atom, it'd look like this. If you had a second atom, you might think that it would put its levels exactly in the same place. It doesn't. It interacts. So what happens is they get shifted like this. One a little higher, one a little lower. Now, as long as these gaps are pretty big, then these are kind of two levels close together. You can call them sublevels. But what happens up here when you get large quantum numbers? You got them very close together. And you bring a bunch more that are very close together. And they split. Well, then they're going to kind of fill in between each other. And then if you get a solid, you have 10 to the 26 of them. They're going to get so close together that for all intents and purposes, they're just filled up. And that's called a band. So bands don't happen down low. They happen on these outer shell guys. And these outer shells have the lowest energy. And they're the ones that match up the low energy photons that you see with your eyes. Which is why you can't look through a solid, but you can look through a gas. All right? So a lot of the properties that explain all about solid-state physics and modern electronics and transistors and lasers are all explained out of quantum mechanics. Which is why it's so powerful for a modern person who's going into engineering today. We don't build things with old-fashioned resistors. We're building things with modern materials. We can adjust by doping the conductivity of a material by 40 orders of magnitude in a modern semiconductor by adjusting these bands, what we call band gap engineering. Frankenhertz, leaving Mr. Bohr for a while. We'll come back to the Schrodinger equation and try to get real power later on. Okay, so Bohr kind of works. Is there any other evidence for this idea that there's a bunch of individual energy levels? And the answer, yeah, there's a real direct one called the Frankenhertz experiment. So in the Frankenhertz experiment, they have a battery up here that runs a current through a filament. And that filament, because it gets heated, has enough energy to exceed the work function and emit electrons. So suddenly you have a set of electrons coming out. If I can find a pin that writes, there we go. All right, so there's some electrons, and they're flying along. And we're actually going to accelerate them this time, make them pick up speed. All right, so they just barely get out, so we put a voltage here. We make them pick up speed. And then at the end, we'll make them slow down, and we'll catch them inside this ammeter, although the second half is somewhat not required. Well, when you do that, what happens is as you accelerate those electrons, they start smacking into things. They knock off some more electrons in some cases. Or they're able to create other ways. And you'll get more of them that will follow the field and get across rather than get deflected out like this or what have you. So you get kind of focused. So what you see is the current will go up. Then an amazing thing happens. If you keep turning up the voltage, instead of constantly getting more or even plateauing, it drops. That seems very strange. It's almost as if the electrons lost some energy and no longer are traveling very fast and no longer get focused over to my plate. If you turn up the voltage further, it starts going up again. And then it falls. And it keeps doing this at equal energies. Now what's happening, and how you can verify this by looking at the lines that are emitted, which happen to match this energy, is that as the electrons go through the gas, they originally don't have enough energy to excite this mercury atom. So it needs about 4.9 electron volts of energy. So when it doesn't have enough, it can't interact. So the only thing that's going on in here is better focusing and getting more of the electrons across the plate. So as you turn up the field, you improve that. But when it hits 4.9 volts, which when multiplied by an E means 4.9 eV of energy, then it has enough to collide and give up all that energy to the mercury atom. So it basically stops. It has no kinetic energy. So it's back down like here. Now some of them don't collide and keep going through. That's why it doesn't go all the way down. But that is why there's this drop. Then it can keep going on. And if it gets enough energy, it can collide again with another atom and excite it. So these steps are because of 1, 2, 3, 4 collisions, and so forth. They've seen up to 10 of them in consistent lines. And when they look at spectroscopy, they see that 4.9 EV line being re-emitted by the mercury. So the energy lost by the electron is also seen as energy given off in a photon from mercury that has been excited. So that was evidence that there was this energy levels that were expected. And that was known as the Franken-Hertz experiment. We have one of those also in the lab. So depending on how much time, maybe we'll do that one too. All right. We're finished with the atom module. Make sure that you can do the Bohr atom. It is by far the main one. I don't expect you to memorize the Lyman lines and the Palmer lines and whatever. Fine, that's all gone out. But I expect you to be able to work with the Bohr atom. And in particular, I expect you to be able to find the energy of the levels, and I expect you to find the radius of the orbits for any type of one electron atom that I give you. It's equal 6, it's equal 8, whatever. Okay? Next module is on wave properties and duality. So we know that the photon is both a wave and a particle. So if I think of the photon as a wave, I say, well, the wave has particle properties. But what if I looked at the motion picture differently? What if I looked at the photon as a particle, matter, and then said, hey, it has wave properties? If I do that, why wouldn't the electron, the proton, and every other piece of matter, including you, also have wave properties? What about the photon is special? A guy by the name of Louis de Broglie decided, said nothing about the photon is special, and makes the following claim. All matter, by that I mean particles, also possess wave properties. They are dual. You only see one or the other property in any part of an experiment. But depending on which experiment you do, depends on which property you see. So for instance, the electron can go through two slits simultaneously because it is a wave. But if you attempt to detect its location by putting up a screen, for instance, and then maybe putting up a small detector where you can find its path, suddenly you don't get wave properties anymore, you get particle properties. If you take the detector out and don't try to find out where its path is, it goes back to looking like a wave. It has both, but it only shows one in any particular experiment that you do. And what you do determines which it shows. If it has a wavelength, the next thing you got to do is have a reason for that wavelength. Now, de Broglie is sitting here thinking about this problem. And the mechanical universe does a reasonably good job on kind of a hypothetical reason for doing it. I'll settle for just the fact that you know the formula. The momentum of a particle is directly related to its wavelength by the following formula. P is Planck's constant divided by the wavelength. Be careful when you calculate P. P is the relativistic mass times V, not the rest mass. Okay? So, it's mv, not m naught v. Now, it could be that m and m naught are about the same, but that's a special case. All right, so be careful. Further, the energy is not Pc. That's for a photon. What is true is this: the energy squared of a particle is E naught squared, the rest energy squared, plus Pc squared. This is always true. That only occurs when this is 0. And that means it has no rest mass. Electrons have rest mass. They have rest energy. The only time you could ignore this is when it's going so fast that this part is so much bigger than that part of the triangle that you can just say, hey, it's this. Remember, this is there's E naught, there's PC, and there's E. You can only say that that is equal to that if this side is basically almost zilch at really high speeds. Otherwise, you can't do that. I go ahead and derive the de Broglie relation and how it's done. Something else to note, it's often convenient to multiply both sides by C because then I get my 1240 eV nanometers again. And if P is in MeV per C, as it is in relativity, multiplying by C kills that and leaves it in units of MeV. So you'll probably want to multiply by C in most cases because it'll save you a lot of time doing conversions. Fine. So it works. Well, everybody immediately believed that what de Broglie did was fabulous and they went off and gave him his PhD. No. Actually, what they did is basically failed him. They didn't give him his PhD because they didn't think that his proof was nearly rigorous enough. But it was also known that this is kind of, cutting edge stuff, and maybe they should go and get some guy's opinion on this. So they contacted this guy by the name of Albert Einstein about this thesis, and he said it looked pretty good, so they gave him his PhD. Not long after that, he won the Nobel Prize. How he won the Nobel Prize was that he got some verification from somebody. And what he got it was from a group called Davidson and Gurman, as well as independently by G.P. Thompson. So Davidson and Gurman's experiment, they were sitting here shooting electrons, banging them off of metal films. Why? They work for Bell Telephone at Bell Labs. And you have electron emitters that strike metal contacts. So this was not only fundamental physics, it was good business. They would then move a detector around, and they would measure that, the number of electrons that scatters as a function of an angle. And when they were originally doing this, they weren't getting any kind of peaks or anything. Well, one night, and I've heard different stories about this. One says they were all drinking in New York. I don't know if that's true or not. I think that's a student would like to believe that. They were out partying, and the vacuum system broke, supposedly, and they got oil on their oil. So what they did with their sample was they decided to clean it, and they tried to clean it, but they knew that it still probably had junk on it, so they decided to heat it. So they heated it. When they heated it, they did something they didn't expect, which is what's called annealing. They turned it into a crystal. They put it back inside the chamber, and all of a sudden, they had these nice humps. Now, it didn't take them long to figure out that there must be some constructive type interference like that that produces humps like that. Well, they were able to shoot photons at this and actually measure the spacing between the atoms and realize that it was crystal. They were able to find this angle. From this angle, they were able to show that they, in fact, had the wavelength expected by de Broglie. So de Broglie won his Nobel Prize for that. Oh, and by the way, Davidson got a Nobel Prize too, as did G.P. Thompson. Questions about the idea that you have a wavelength. All particles have them. You, me, whatever. So why don't I see you looking wavy?
Because you're seeing us?
Huh?
Because you're observing us?
Well, I'm observing you, true, but I should be able, if you have a wavelength and you walk through that door, you should diffract and bend around the door, right? And you might even, unfortunately, diffract through two doors as you walk through one, and thereby eliminate yourself. You do not look like you have a wavelength. Why not?
Really long.
Small.
Where? It's small, okay? So if you have a wavelength that turns out that I can't see it, just like the N before that we had, then it doesn't matter if it exists because I have no way to detect it. All right? With electrons, we have spacing small enough to see their wavelengths. Go ahead and try to figure out what the wavelength of something that's a little larger is. And I gave you a problem like that. The problem I gave you was this. You're going to connect the wavelength of a baseball. I love baseball. You may know that by now. Anybody played college ball and coached it likes baseball, right? So determine the wavelength of a quarter-kilogram baseball moving at 30 meters per second. Now you got to do a few questions. First one you got to ask yourself is, do you need relativity on this problem? I got a lot of no's. Why not?
Because it's going
30 meters.
And it's going at such a small fraction of light speed that
Bingo. It's going such small fraction of light speeds, way below 1/10 of the speed of light. So, no. But you need to ask that because a lot of particles in a problem will, and if you don't use relativity, you get the problem wrong. Okay? Next, calculate linear momentum. Well, that's pretty simple. That's m naught v in this case, because m is m naught, they're not using relativity. 0.25 kilograms, going at 30 meters per second. Let's take my calculator and punch it, and store those easy points in my back pocket. It'd be almost criminal to get points for this. And then the only part that's really this course is find the de Broglie relation. Okay. So P is H over lambda. So lambda is H over P. Now here's an example where you don't want to multiply by C. This is a big object. So SI units make sense to work on such thing. It also tells you should be using quantum mechanics again. 6.6 by 10 to the minus 34 joule seconds. And on the bottom, 7.5 kilogram meters per second. And you get the incredibly giant wavelength of 8.8 by 10 to the minus 35 meters. Far less than the size of the nucleus. So therefore, even though it exists, you're not going to see it. All right, total waste of time. So let's give you something where you would see it. Give that time. Okay. 2 GeV electron from the Stanford Linear Accelerator Facility. Now here we got something that flies. Okay. Oops, let me bring that. Do we need relativity? Yes. Okay, it's much, much greater than E naught. What's the rest energy of an electron?
0.511.
So what?
0.511 keV.
MeV. All right, half an MeV. So this thing's got 2,000 MeV. All right, so it's about 4,000 times the rest mass energy of an electron. So it is way the heck. 20 kilovolts on a flyback transformer in a television set, you need to use a relativity for electrons. And in fact, the emission patterns of where the radiation goes is actually altered, if you don't think about that. So in this case, it's very relativistic. Now the good news is, it's so relativistic that you basically can ignore the rest mass energy. So E squared, which is E naught squared, plus PC squared, is just approximately PC squared. This energy here is so heavily dependent on the 2 GeV. There's 2 GeV plus point, okay, there's 2,000 MeV plus 0.51 It's still about 2,000. So you can just ignore this because you're going to square it. All right? So this is just about that. And that's why the high energy particle physicists, they don't distinguish between mass, momentum, or energy. When they talk about the mass, they'll say, oh, that's 2 GeV per c squared. When they talk about the momentum, oh, that's 2 GeV per c. And when they talk about its energy, it's 2 GeV. If you just let c be 1, they all have the same freaking units. All right? That's kind of the way they act. All right? They don't even worry about the difference between. That's because they're always so fast that E naught is irrelevant in their problems. That's really kind of bad to be getting in those habits, but that's what they do. So E is approximately PC. So P is approximately E over C. That was nice. Didn't have to punch in nothing about the electron anywhere in the calculation. Now to calculate lambda. Well, lambda is equal to H over P. Well, okay, that's going to be HC over 2GeV. Or 1240 MeV picometers, I'm sorry, Fermis, over 2,000 MeV. About 0.62 Fermis, or 0.62 femtometers. If you prefer that. Important thing, the more momentum, the smaller the wavelength. The smaller the wavelength, the smaller the object you can look at. So if I want to look at something very small, I'm limited with optical wavelengths. But I'm not limited if I use electron wavelengths, hence the electron microscope. And I'm going to go down below the size of the nucleus, I need wavelengths smaller than the nucleus, which is why you're going to need GeVs and higher in order to look down there. 2 GeV won't do it today. We got to go even higher because we want to look even closer at smaller distances. So we need bigger, bigger, bigger machines. And that's why we need bigger, bigger, bigger machines. Let's try one that's a little different. Problem number 3. It asks you to calculate the wavelength, but this time it's only 20 electron volts. So the question we start off is, what?
So we need relative.
Is it relativistic? And what's the answer to this one? I got some shaking heads. What's the words for that?
No.
No. Okay. It's only 20 electron volts, and the rest mass energy is 511,000 electron volts. So this is not a relativistic. This is a low-speed electron. So that means we can use the kinetic energy formula, P squared over 2m, which I could not have done in the previous problem. So I got to know that in order to calculate P correctly. That's the key thing here. That's why there's 2 different problems. Not relativistic. E naught is much greater than K. Therefore, K is P squared over 2m naught, or P is the square root of 2m naught times K. Now again, it is convenient and useful to multiply top and bottom by c squared so as to convert that mass into the rest mass energy. So if I was to take and multiply this by 2 m naught c squared times K, then I would need to divide that by c. I have an energy under a square root. I'm going to get an energy out divided by c. So I'm going to get MeV as per c. I'm going to get an EV per c in this particular problem. Okay? So let's go ahead and do that. P is the square root of 2 times 0.511 times 10 to the 6th EV times 20 EV over C. Now why did I choose to do that? I chose to put this as an even power because the square root will simply divide the exponent by 2. So that means there's going to be 1,000 coming outside here. So if I take that 1,000 out, I got a keV per C. I got 2 times a half, that's about 1, times 20. So I'm looking at about the square root of 20, a little more than 4, so it's about 4 keV per C. You want to be able to make quick calculations in your head to check your work. Get used to practicing dealing with exponents. When you have square roots, try to get the exponents so they'll be even. Then you can divide by 2 and pull them out. So 2 times 0.51 times 20. Second square root, second answer. 4.52 keV per C. All right. Then we got P is H over lambda. Or lambda is HC over PC, if you prefer, whichever. And I get 1240 keV picometer. And when I multiply P by C, I get rid of the C, 4.52 keV. So I'm about 1,200 divided by about 4, that's about 300 picometers. .74. 274 picometers. Now remember that the X-rays were up in the picometer range. So this is an X-ray wavelength. So you have got an electron here that has a small wavelength. But let's look at it in terms of other things. Okay, that's 10 to the minus 12, 10 to the minus 11, 10 to the minus 10. I could have also written this out. 2.74 inches. Notice that the wavelength is the size of an atom. And this is what they're giving atoms their size. All right? It's not by chance. There is a connection between size and energy. Things that are very energetic have very small size and they're located in very small boxes. And things that are larger have less energy and they take a bigger space. As you get an outer electron, it takes a bigger space. It's not because of orbits, it's the wavelength that is determining them. And that's what the attempts to do next was to show how constructive interference of wavelengths explains the Bohr atoms. They're the place where the electron orbit, or electron wavelength, in essence, constructively interferes with itself. And if it's not on one of those orbits, it can't constructively interfere with itself. And I think that's probably about all the time we got. So I'll see you guys on Wednesday.